we start the third unit, that is the physical chemistry. Third unit, it is with the physical part. Okay. So in this physical chemistry, first we discuss about the black body radiation. First topic is the a body, it emits the radiation, so that radiations are appear in black in color, so then it is known as a black body radiations. So why these radiations are appear in black means a black body, okay, a black body radiation, that visible region, okay, that visible light, it will be appears rather than the reflect. So due to that reason, on that surface appears in black in color, okay, that's why these are black in color. Okay, so black body radiations, okay, the radiations are appear in the black in color. A black body, okay, here we take the one body, okay, that is considered as a black body. Okay, so this body, it absorbs all the electromagnetic radiations, okay, it is ready to absorb the all electromagnetic radiations. Okay, it absorbs the all electromagnetic radiations at all wavelength. Okay, so then it is known as a black body. Okay? A black body means it is a perfect emitter, so it emits all the radiations, means it is a good emitter. So then here it forms the emission spectrum at the given temperature. So according to Boltzmann, it is the power, it is directly proportional to the fourth power of the temperature. So it emits, it forms the continuous emission spectrum. So generally a hot body, it emits the radiations, okay, it emits the radiations, okay, it emits maximum all the radiance, okay, it absorbs that at high frequencies. So in which it emits a high frequencies, so at that time here it is with the low wavelength and longer frequency. But here black body, it emits the same radiations at the given temperature. So that phenomena is the color object. That phenomena is the color object. So in that color object, generally in infrared, IR region is known as the infrared region. This infrared region, that object, it appears in the red in color, and in the UV region it is in the yellow. That is known as a black body radiation. Black body radiation means here the body, it absorbs all the electromagnetic radiations at all wavelengths, is known as a black body radiations. Heat capacity. So heat capacity means we take one solid. Here we take, for example, it is the solid. This solid, it is maybe palladium or scandium or something, any. Here we take the one solid. So in this solid here, we increase its temperature. Temperature is increases at 1 degree centigrade. How it is increased? By supplying the heat. Means here the minimum amount of heat is required to rise 1 degree centigrade temperature in a solid, that is known as a heat capacity. Okay, so that substance, okay, here the substance, it is the 1 kilogram of the solid. That solid, it is the 1 kilogram of the solid. Means here the amount of heat is required. So 1 kilogram of solid is increases to 1 degree centigrade. It is known as a specific heat capacity. Otherwise here the solid, it is the 1 mole of solid. 1 mole of solid, it needs some amount of heat to rise 1 degree centigrade temperature. So then it is known as a mole of heat capacity. So according to Dulong-Petit, the mole or heat capacity of a solid, so approximately it is at 3 R at room temperature, 3 R at room temperature. And according to Einstein, here, he suggested temperature is decreases, okay, so then automatically heat capacity is also decreases. Okay, temperature is decreases, heat capacity is also decreases, and then it nearly approached to zero also. It is approached to zero. Okay, it's said by Einstein. And finally here, Debye suggested is Debay's law. It gives accurate values to express accurately. It will explain the vibrational mode. Okay, it is explained in vibrational mode of crystals. So then here it explains very clearly. Okay, very accurately. So here heat capacity means here we take one solid. Okay, in that solid we increase its temperature at least 1 degree centigrade. At that time here we need some amount of heat. That is, heat is known as a heat capacity. So here in 1 kilogram of the solid in which we increase the temperature 1 degree centigrade, it is known as a specific heat capacity. Molar heat capacity means solid, it is the 1 mole of the solid. According to Dulong-Petit, here that heat capacity of the 1 mole of the substance is at approximately, it approach to the 3 R at room temperature. And according to Einstein, temperature is decreases, its heat capacity is also decreases, and also it approach to zero. And finally, Debye he suggested and he explained very accurately. So he considered the vibrational mode of the crystals. Okay, it is a Bunsen burner. It is help to it produce the heat. Okay, here we take that operator. So inside here it is one more tube is there, and here it is closed, and in this tube here we arrange the one thermometer, and here it is with the solid. Okay, here it is the solid. So here it is the boiler. It is the boiler. So now here we supply the heat from here. So first that boiler it receives the heat, then it enters into that solid. So here this solid it receives the minimum amount of the heat. So that solid it is converted to liquid. Okay, the solid it is converted to liquid. So after converting of the liquid, here this thermometer is there na. So this thermometer it detect the how much temperature it utilized. Okay, means here it reached 1 degree centigrade, it indicate it reached the 1 degree centigrade. Okay, so here this graph it is the heat capacity, and in this axis here we take the temperature. Okay, first we take the solid. Okay, here it is the solid. Solid is converted to a liquid. So then liquid is converted to a gas. Okay, solid it converted to liquid. The temperature is remains constant. Okay, here the temperature it remains constant when here that solid it completely turns to liquid, means here it is a solid. Okay, in that solid molecules, in all the molecules, okay, that solid it completely convert to liquid. Up to that here the temperature is constant. Once this total complete all solids are converted to liquid, then here temperature is also changed. Okay, otherwise here it maintains the same temperature. Okay, it is about the heat capacity. Next one, that is the Rayleigh-Jean's law. So this Rayleigh-Jean's law it is useful to this generally it is a physical chemical formula. Okay, it is a chemical physical formula. It is useful to describe the black body radiations. Okay, it is useful to describe the black body radiations. Generally here in which its electron density is increases. Okay, in which electron density is increases with frequency and pressure. Okay, in which that electron density is increases with its frequency and temperature. Okay, so generally here this here its formula is the T is equals to 8 pi squared mu squared by C cube kT. Okay, it is the Rayleigh-Jean's law formula. So these U, V, T, these are the spectral electric densities, okay, spectral electron densities. Okay, here it is the mu is the frequency and c is the speed of the light and k is the Boltzmann constant and t is the temperature. Okay, t is the temperature. So this law, it is useful to explain at low frequency and long wavelength. Okay, this law, it is useful to explain only at low frequency and long wavelength, but it failed. Okay, but it failed to explain at high frequency. Okay, it is failed at high frequency. Okay, so due to that, it leads to the ultraviolet catastrophe. Okay, so due to that, here it leads to the ultraviolet catastrophe. Okay, so it is about the Religion's law. Okay, this Religion's law here, it explains only at low frequency and long wavelength, but it is failed to at high frequencies. So due to this, here it leads to the ultraviolet catastrophe. Okay, next one is the Planck's law. So this Planck's law, it is useful to explain the electromagnetic radiations. Okay, it explains the electromagnetic radiations. Electromagnetic radiations. It is useful to explain the electromagnetic radiations by applying the, okay, by applying the black body radiations, with thermal equilibrium. Okay, with thermal equilibrium. So here is all resolving the quantum, okay, that is the energy quantitization. Okay, energy quantitization means the photons. Okay, energy quantitization means the photons. So here it is at high frequencies. Okay, here it is at high frequencies. So then here it also leads to, okay, due to that reason, here also it leads to the ultraviolet catastrophe. Okay, so here this Planck's law, here mathematical part is there. That mathematical form of this Planck's law is the BVT equals to 2h nu 3 by c square into 1 by e to the power of k minus bt minus 1. Okay, so here it is the mathematical form of the Planck's law. Okay, it is the spectra radiance. Okay, BVT is the spectra radiance. So h is the Planck's constant, c is the speed of the light, and here B is the Boltzmann constant, T is the absolute temperature. Okay, it is the mathematical form of the Planck's law. This Planck's law, it successfully explains the black body radiations. Compared to remaining laws, here it successfully explains the black body radiations. So black body radiation means, so it absorbs all the electromagnetic radiations at all wavelength. Okay, and also this Planck's law is also known as a universal law. Why it is called as universal law means, this law, it explains that all that radiations at all wavelength and at all metals. So that's why it is considered as a universal law. And another important significance of this Planck's law is the, it is successfully explain the absorption of the heat and that color formation. So generally here the object, it is heated. Okay, the object, it is heated. So then here it appears in different colors. Okay, here it appears in different colors. Example, here it appears in the, first it appears in the red color. So after red color, then here it turns to the yellow color. After yellow color, again it turns into the white color. So here this Planck's law, here it explains why here it that hot body, it shows that different colors on heating. So simply here it is due to the wavelength. Generally temperature is increases. Okay, temperature is increases, its wavelength is decreases. Okay, due to that decreasing of the wavelength generally, so this red color, it is absorbed at the high wavelength and white color is absorbed at the low wavelength. Okay, that's why here temperature is increases, wavelength is decreases. So that's why first temperature is increases, it turns to red color. Again we increase the temperature, it turns to yellow color. Again it is increases, it turns to the white color. Okay, simply means here it is important that temperature is increases, wavelength is decreases. It is about the Planck's law. Planck's law is known as a universal law. Why? Because here it explains all that electromagnetic radiations at all wavelength and at all. And next one is the photoelectric effect. So photoelectric effect here. First here we take the one vacuum tube. Okay, here it is a one vacuum tube. Okay, in this vacuum tube here we keep one metal. Okay, so here it is the metal. That metal it is maybe antium or rubidium or potassium, any metal. So then here opposite that metal here it is one is the detector. It is the detector. So these two are connected, first ammeter. Okay. So then here it is connected to the battery. So from here we pass the light. Okay, it is the light, beam of the light. Clear? So here a beam of light, it stick the metal surface. So then what happened here? This metal it eject the electrons. Okay, this metal it eject the electrons means it release the electrons. So how to identify the formation of the electrons? Here detector is there. Na? The detector it detect that formation of the electrons. Okay, so the beam of light is passed on the metal. So then here it eject the electrons. That is known as a photoelectric effect. Okay, it is known as a photoelectric effect. So here, see here, the beam of light is passed on the metal. Oh, here it stick the metal surface. So and here ejection of the electrons, okay, sticking of the light on the metal surface and the ejection of the electrons, both are takes place simultaneously. Okay, here both are takes place in simultaneously, means there is no any time gap. Immediately here this light is stick on the metal surface, immediately here that metal it produce the electron. There is no any gap. Okay, in this. And here another thing here, the number of ejection of the electrons. Okay, the number of ejection of the electrons means the releasing of the electrons are directly proportional to the intensity of the light. Intensity of the light means here light intensity is more. Okay, light intensity is more, so then ejection of the electrons is also more. Okay, so that's why number of ejected electrons are directly proportional to the intensity of the light. That electrons are ejected. Okay, so released. So here that ejected electrons are with some energy. Okay, so here some frequency that is known as a threshold frequency. Okay, these are with minimum frequency. These are with minimum frequency. So that minimum frequency is known as a threshold frequency. That is known as a threshold frequency. So below the threshold frequency, okay, so here this photoelectric effect is not possible. Above the threshold frequency only, here this photoelectric effect is possible. So here these electrons are ejected. Now that electrons are with kinetic energy. These are with kinetic energy. Generally, this kinetic energy is increases, the frequency of intensity of the light is also increases. Okay, kinetic energy is increases, the frequency of intensity of light also increases. Okay, so photoelectric effect means, so a beam of light it passed on that metal, immediately it release or eject the electrons. So here the both are takes place simultaneously, that is known as a photoelectric effect. So in which the number of ejected electrons are directly proportional to the intensity of the light, and that electrons are with minimum frequency, that is known as a threshold frequency. Okay, below the threshold frequency, it is that photoelectric effect it is not possible. And also here these are with some kinetic energy, okay, that electrons are with kinetic energy. That kinetic energy is increases, the frequency of intensity of that light is also increases. It is about the photoelectric effect. Next one, that is the limitations of the classical mechanics. Okay, next one is the limitation of classical mechanics. Limitations of classical mechanics. Generally, in everyday objects, okay, so this classical mechanics explains greatly, but these are failed to explain microscopic particles, microparticles like atoms or subatoms, and high speed. High speed means light speed, and also greater means high, greater gravity levels. Okay, so generally in daily objects it is explained vastly, but it failed to explain in the microparticles like atomic and subatomic particles, and high speed like light particles, and also great means high gravitational levels are unable to explain the phenomena of the black body radiations, photoelectric effect, and also why that atoms are with more stable. Okay, so here it is resolving. Okay, here it resolving the, and that quantum mechanics. Okay, it is resolving that quantum mechanics and also it concepts. Okay, quantum mechanics and also it concepts. So it it treats that energy. Okay, it treats that energy motion. It is unable means it is continuously. Okay, here that energy and motion, so it is continuously move. That quantum mechanics, okay, the resolving of that means the requiring of that quantum mechanics and its concepts, these are helpful to explain that and the treating of that energy and motion continuously. Okay, these ignore that wave particles also. Okay, here it ignores that wave particles also. So these classical mechanics are failed to explain the black body radiation. Black body radiation. Generally, black body radiation means a body it absorbs the energy. Okay, a body it absorbs the energy means electromagnetic radiation at all wavelength. But this classical mechanics, these are fail to explain how that the energy is distributed. Okay, that hot body it release the some radiations, how it is distributed in that. Okay, it is one limitation. And next is photoelectric effect. Okay, it fails to explain the photoelectric effect also. Okay, this classical mechanics are fail to explain the photoelectric effect means the metal it release the electrons. Okay, here it explains only the beam of light. Okay, the metal it absorbs that beam of light, then it ejects the electrons, but it failed to explain about the intensity of that metal. It failed to explain that atomic and spectrum. Okay, it is the absorption and atomic spectrum. Generally we know that electrons are revolved around the nucleus. Okay, so it explains that electrons these are revolved in the nucleus. Okay, but here it fails to explain that how to form that line spectrums and absorption spectrum. And also another thing here, it failed to ignore the wave particles. So it is about the limitations of the classical mechanics. Next one, Compton effect. So this Compton effect, okay, this Compton effect, it is the quantum spectrum, okay, it is the quantum theory of the spectrum. So this quantum theory of the spectrum, it explains, means here it is based, explains means here it maintains the interaction with the charged particles, okay, here it maintains the interaction with the charged particles. So here this charged, this Compton spectrum, these are with the charged particles. Generally, these charged particles of that Compton scattering, here it maintains a good relation. Okay, here it maintains a good relation with the electron. So at that time, it maintains the high intensity, but the same time here, slowly it starts the disturbances in that protons. So due to that disturbance, that electrons, that loosely bounded electrons are present in the valence shell, these are ready to remove. Okay, it is known as a Compton effect. This Compton effect, it is applied in some unusual results appear. So for example, this Compton effect classical theories are applied in the X-rays. Okay, that X-rays, so the same one single material, we can take the number of X-rays. So at that time we apply this classical theory of that Compton effect. It is about the Compton effect. And next one is the de Broglie wave equation. Okay, so de Broglie wave equation, it explains the wave nature and the particle nature. Generally in everyday objects, these are with, in which they maintain the relation with momentum and the wavelength, that is the lambda equal to h by p. So p is the momentum and mu is the wavelength. So according to this law, it maintains the relation with momentum and wavelength. De Broglie law, okay, de Broglie hypothesis. And next one, that is the wave nature or the wave particle nature. Generally a matter, if we consider the matter, matter means it is not only single wave nature or particle nature. Matter means it contains both the particle nature and also the wave nature, then only it considered as a matter. Otherwise it is not considered as a matter. So these also known as a wave motions, otherwise motion waves. It is suggested by de Broglie, that's why these waves are also known as a de Broglie waves. Okay, these are also known as a de Broglie waves. Generally this type of wave particle natures are used in the fundamental techniques. For example, that electromagnetic microscope, it is very important microscope. So in that microscope we apply this wave particle natures. These are not possible to vision, but these are very fundamentals in that techniques. That's why these are used in the electromagnetic or electronic microscopes. Next one is the Heisenberg uncertainty principle. Generally it is known as uncertainty principle. It is developed by Heisenberg. According to Heisenberg uncertainty principle, the exact position and momentum, so it cannot be possible to know at the same time. That is known as a Heisenberg uncertainty principle.